32 meters beneath the streets of the Ile-de-France, a machine weighing 2,200 tons is advancing through Letitian limestone at a rate of approximately 12 meters per day. Behind it, robotic arms lift prefabricated concrete segments into position, locking them together to form a tunnel lining that must remain structurally sound for the next century. Ahead of it, sensors monitor the geology in real time, adjusting the cut-ahead pressure and rotation speed to match the ground conditions. This is one of 27 tunnel boring machines currently operating beneath the Paris metropolitan area. Together, they are constructing 200 kilometers of new rapid transit tunnel, the largest infrastructure project in Europe. The Grand Paris Express comprises 4 entirely new automated metro lines and extensions to 2 existing ones, adding 68 stations and connecting suburbs that have never had direct rail links to each other. The budget, originally set at €18.3 billion in 2010, now exceeds €42 billion. The first section opens this October. Whether this project represents visionary urban planning or catastrophic financial mismanagement depends almost entirely on what happens in the next 4 years. The Paris Metro opened in 1900. It was designed to move people between central Parisian arrondissements, and it performs that function well. 14 lines, 308 stations, and 5 million daily journeys make it one of the most heavily used urban rail networks in the world. But the Ile-de-France region has changed fundamentally since the metro was conceived. 70% of its 12 million residents now live outside the périphérique, the ring road that defines the boundary of the city proper. Major employment centres, La Défense, Saclay, Roissy, Orly, sit in the suburbs. The existing network is radial. Every line passes through the centre. To travel between 2 suburbs on opposite sides of Paris, say from Saclay to Roissy, a commuter must take a bus to the nearest RER station, ride into central Paris, transfer, ride back out, and potentially take another bus at the far end. A journey of 30 kilometers can take 90 minutes or more. The Grand Paris Express is designed to solve this by building an orbital network, a set of lines that connect the suburbs directly to each other, bypassing the city centre entirely. Line 15, the backbone, forms a complete ring around Paris with 33 stations. Lines 16 and 17 extend north and east to connect growth areas with Charles de Gaulle Airport. Line 18 runs south to link Orly Airport with the Saclay Research Cluster. 2 million passengers per day are projected across the network. The concept is sound. The execution has proved significantly more difficult than anticipated. Paris presents a tunnelling environment of exceptional complexity. The city sits on a geological sequence that varies significantly across short distances. Limestone capable of supporting tunnel boring in one section gives way to sand, then clay, then gypsum, sometimes within a single kilometre. This variability is compounded by the density of existing underground infrastructure. The metro, the RER, the sewer network designed by Eugene Belgrand in the 1850s, water mains, electricity cables, telecommunications fibre, and gas lines all occupy the first 20 metres of subsoil. The Grand Paris Express tunnels must thread through this at depths of 25 to 45 metres. And then there is the specific problem of the Paris quarries. Between the 13th and 19th centuries, limestone was extracted from beneath Paris to build the city above. The resulting network of tunnels extends for over 300 kilometres. Some sections were converted into the famous catacombs of the late 18th century, when overcrowded cemeteries were emptied and the remains of approximately 6 million people were transferred underground. Not all of these quarry workings are mapped. Where the GPE tunnels intersect quarry zones, ground consolidation must be carried out in advance, injecting grout or concrete to stabilize voids that may not be precisely located. This is slow, expensive, and occasionally surprising. A more insidious challenge is posed by the gypsum deposits in the northern sections of the route. Gypsum is calcium sulfate dihydrate, a mineral that dissolves readily in water. When groundwater flows through gypsum beds, it creates voids. If those voids are large enough, the surface subsides. Tunneling through gypsum requires constant monitoring of groundwater levels, and, in some cases, pre-treatment of the ground with injection techniques to seal potential dissolution pathways. The tunnel boring machines operating in these zones are multi-mode EPB shields capable of switching between earth pressure balance mode and slurry mode, depending on the ground conditions encountered in real time. Heron Connect supplied 27 tunnel boring machines for the project, 23 EPB shields, and 4 multi-mode TBMs, with diameters ranging from 7.7 to 9.8 meters. Each machine is over 100 meters long when its trailing gantries are included, and operates with a crew of approximately 12 per shift. The naming convention, incidentally, is worth noting. Each TBM is named after a notable woman: scientists, artists, activists. The machine currently boring Line 15 East is called Marine, after the marine biologist and environmentalist Anita Conti. At peak activity, multiple machines were advancing simultaneously on different sections of the network, generating millions of tons of excavated spoil that had to be removed, processed, and in many cases recycled as aggregate for concrete production elsewhere on the project. The 68 stations present engineering challenges distinct from the tunnels. Many are located at depths of 30 to 40 meters, requiring excavation of caverns that are, in structural terms, closer to underground cathedrals than to conventional metro stations. Each station must accommodate platforms for automated trains, ventilation systems capable of handling emergency smoke extraction, escalator banks, lift shafts, and the system's infrastructure for fully driverless operation. Construction has been complicated by the discovery of archaeological artifacts on multiple sites, medieval foundations, Roman-era pottery, and in one case, a section of ancient road that required documentation before work could proceed. Due to delays on Line 15 South, Line 18 will become the first of the 4 new Grand Paris Express lines to carry passengers. The initial section, from Massy-Palaiseau to Crisse-de-Saclay, is scheduled to open in October 2026. Line 18 is unusual within the project because the majority of its initial section runs above ground, carried by a viaduct close to 7 kilometers long, the longest rail viaduct constructed in France. While the rest of the Grand Paris Express is buried deep beneath the suburbs, Line 18 crosses the Saclay Plateau on elegant concrete piers. In May 2025, the first fully automated train set was delivered to the Palaiseau Operations Centre. These are grade of Automation 4 vehicles, the highest level of railway automation, with no driver and no attendant on board. Acceleration, braking, door operations, obstacle detection, and platform alignment are handled entirely by the onboard control systems. 15 train sets are being delivered under a contract worth €199 million with Alstom. 10 will serve the opening section, with 5 reserved for the planned extension to Orly Airport, which is targeted for late 2027. The strategic logic for prioritizing Line 18 is rooted in economic development. The Saclay Plateau hosts one of France's highest concentrations of research institutions. The CEA, École Polytechnique, Paris-Saclay University, and numerous associated laboratories and technology companies. These institutions employ tens of thousands of researchers, many of whom currently commute by car due to the absence of direct rail connections. Line 18 is intended to do for Saclay what the original metro did for central Paris: make a concentrated cluster of activity dramatically more accessible, and in doing so, make it more productive. The financial trajectory of the Grand Paris Express is, by any measure, concerning. The original budget of €18.3 billion has more than doubled. A technical audit published in 2024, the Ramit-Bentz report, identified serious coordination problems between civil engineering contractors and system integrators, particularly on Line 15. Line 15 South, the flagship orbital line, was originally scheduled to open before the 2024 Paris Olympics. It has been postponed repeatedly and is now expected in spring 2027, 3 years later. The delay is attributable primarily to the complexity of commissioning a fully automated railway system where multiple contractors are responsible for different subsystems that must function as an integrated whole. These problems are not unique to the Grand Paris Express. London's Crossrail project, now the Elizabeth Line, was 4 years late and billions over its original budget. It is now one of the most popular railway lines in the United Kingdom, with ridership consistently exceeding forecasts. Copenhagen's driverless metro, the Cityringen, experienced similar delays during construction. Today, it is the backbone of the city's transport network. The historical pattern is consistent. Large urban transit projects almost invariably overrun on cost and schedule, and almost invariably prove their value within a decade of opening. The Grand Paris Express is a bet, an extremely expensive one, that the same pattern will hold. That €42 billion, amortized over a century of operation, will prove to be the cost of transforming a 20th century city into a 21st century one. When complete, the network will operate 183 fully automated trains manufactured by Alstom. Line 15's trains are 6-car sets, 108 metres long, capable of carrying 960 passengers. The full orbital ring will have an operational frequency of 2 to 3 minutes between trains during peak hours. The complete network, all 4 new lines plus the extensions, is projected for completion between 2030 and 2031. Whether that timeline holds will depend largely on the lessons learned from the current commissioning difficulties on Line 15 South. The Grand Paris Express matters beyond France because the problem it addresses is universal. Suburban sprawl without adequate transit is the default condition of most major cities in the developed and developing world. Car dependency, congestion, and carbon emissions are the consequences. If Paris demonstrates that a 200-kilometre automated metro network can be constructed beneath a medieval city, through catacombs, quarry voids, and dissolving gypsum, past Roman ruins and medieval foundations, it establishes a precedent. It proves that the engineering is possible, even under conditions that are, arguably, as difficult as any urban tunnelling environment on Earth. Somewhere beneath the Ile-de-France, a 2,000-ton machine is advancing through limestone that was laid down 50 million years ago, in a sea that covered what is now northern France. Behind it, robotic arms are assembling a tunnel that is designed to carry passengers for the next 100 years. Above it, 12 million people are conducting their daily lives, most of them unaware that the largest construction project in European history is taking place directly beneath their feet. In October, the first passengers will board a driverless train on a viaduct over the Saclay Plateau. It will be unremarkable in the way that good infrastructure always is: quiet, reliable, and taken for granted within months. That is the nature of transit engineering. The highest compliment it can receive is to be forgotten.